This is what we have at our disposal. Obviously, we are trying to do some modeling, so we need to ask ourselves the right questions. Do I want to do supervised learning or non-supervised learning? And then, given these, which one should I use? So, my first hint here is we're going to start with supervised learning. Supervised learning is the fact to show some labels or to show some values to the model, and then the model tries to match that value as closely as possible. The non-supervised learning is slightly different. You don't show the models the target you want to reach. You just give it an insight about distances or dissimilarities between points and ask the model to find a way to group data together. So that's two different approaches. Here we're going to use the first one, the supervised approach. And then amongst the supervised approach, when we have defined this, what do we want to use? Neural networks, random forest, XGBoost, CatBoost. There are many other ones that I haven't listed. And my advice is that it depends on your objective, but also on the way you understand the models and which models you are comfortable with. So let's take a look at our objective. If I go back here, I have done my data set for my explanatory variables, so the variables I'm going to use to predict my targets, but so far the targets have not been defined. So let's take a look at that. I've said that I'm going to use classification. So classification is the fact to predict a label rather than a value. And here I will explain later why I'm using classification, but the fact that I'm using classification is very linked to the type of model I'm trying to build. One thing we need to be aware of is the way we build these labels. So it's very easy in financial forecasting to introduce what's called a forward bias looking error or bias to the model, meaning that we have introduced some data that is not available at the time when we want to make the prediction. Typically today, I don't know what the value of the S&P will be tomorrow. That would be a good insight, but it's not possible. So when we are trying to assess our model in the past, we need to be in the exact same conditions to this, and we need to make sure that we don't use data that were slightly ahead of time and then improve dramatically our model and our predictions doing that. So that's why I've said here that I'm going to lag my label. So let's just run the example of this label. I am going to look at the trend, 3 months trends in the Brazilian stock market. So as we're talking in business days, 3 months is roughly 62 days. Here I'm defining my label. Let me just run it, and then I'll explain what it's doing. This is not useful when we are in this environment. And here I'm plotting my labels. So let's go back to this. What does it do, and why can I do that? So first of all, what it does is that it determines trends in the data based basically on the 3 months returns. Okay, so I'm saying what's the return is on a 3 months rolling basis, and depending on the sign of the returns, I say that it's a uptrend or a downward looking trend, downtrend. So the labeling is not perfect, but it's not dramatically wrong. Here it's going up, and we see that it's up. Here it's going down, and we see that it's labeled with -1. And if we go like this throughout, you see that most of the time it's pretty much in line with what we would expect to do. Sometimes it doesn't manage to do it because there is much noise in the data, and it doesn't know which direction it goes. It flips around very quickly. But it's very important to spend time to define correctly the labels that you want to use for your machine learning model, because the model is only learning what you tell it to learn. Here I want to look at trends. Indeed, if you many people use very short-term forecasting. For example, if you use, I don't know, 5-day forecasting, which I'm not going to use here, it's just to show you you obtain something like this, which is very noisy. So your model is going to have much more trouble into defining the correct labels, and more specifically, as you are going to build a strategy upon that, upon those forecasts, it's going to be very difficult to execute the strategy if the model flips sign every day or every other day, and then you don't have time to execute your strategy and to clip your gains. If you are forecasted for 5 days return, you need to at least to give it 5 days before you can close your positions. But if the signals turn after 1 or 2 days, then you have overruled your own system. So it's very important to keep in mind that that what you are trying to learn is something that you need to be able to implement in a strategy. So let's go back to our 3 months trends here. And then I'm going to merge that to the data set we have already. So I'm just calling it labels, and I append it to the right. And so my data set now is fully ready to be fed in a model. Let's take a look. So let's take the tail rather than the head. So the tail is the end of the data, of the frame. And you can't see it here because I've lagged the prediction. I've lagged the label by 1 day. So as I explained, not to introduce any forward bias, I've made sure that the labels are lagged by 1 day on top of the forecasting horizon, so that we don't predict things that we cannot predict with available data. As we've seen before, as a quick example, here we go. We have, for example, CAC here in France, and we have some data that is based in the US. The VIX is computed from US stock markets. So if we don't make sure that the data is correctly labeled, meaning that I cannot trade CAC with the data of the VIX, because the VIX is published after the close of the CAC, then I'm introducing a forward bias that might seem not very obvious visually, but actually that is going to heavily skew my model and heavily bias it, and then the model would not be exploitable. So that's why I'm lagging all the labels by 1 day to make sure that there is no such problem in my model. So back to the modeling. I have my label, I have my data. Now it's about choosing the right model, choosing the right architecture, and trying to learn as much as we can from the data. So I have prepared a small script here for you, just to show you how I came about to choose the architectures. And here I have a small question for you. Is, can you guess where the missing points should be? What I've done is I've just plotted a sinusoid here, and I've randomly taken out a few points. And anyone here can very easily spot where the points are missing, and you can easily, in your mind, just interpolate between those points. And this is exactly a problem that you can introduce in your machine learning model. If you show this kind of data to your machine learning model, you will have zero trouble connecting the dots. Basically, it will very easily learn how to plug the holes, and your model will have a very high accuracy. So it will look very good. However, is that really the case? Is that really the case? Meaning that, do you have any insights to what's happening outside from this graph? What's happening after the 100 here? Just because you were able to plug the holes here, 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 here. Actually, you don't, because if it goes down like that, your model that has been able to plug the holes here will not know what to do here on a downward trending sinusoid. Let me just illustrate this with a very short script. which is basically where I got my image from. So I'm just drawing the sinusoid. Here I'm just excluding 30 points from it. I'm just plotting the new ones. So that's how I got my my sinusoid you saw on the slide. Obviously, you can easily plug the holes, and the machine learning model can also plug the hole. However, how does it behave if you do this correctly and you don't just tell it to learn what's happening within the missing part, but you're telling it what's happening after the 100. So you have to imagine that the x-axis is a time-based axis. What's happening after the 100? And then let's see what happens. So what I've done later here is I've just redone the same sinusoid, but I've put more points. So rather than 100, is to 1,000. Here we go. So this is the view. This is what I'm trying to predict, and I am going to do some splitting between a training and a validation set. So what I'm going to do is I'm going to select the 700 first points and try to predict the last 300 points. Okay, so from 700 to 1,000. So what does it look like? I'm just splitting that up, and now I'm going to use a random forest. So random forest is a model that is called an ensembling model. So it's basically doing an average of something, and it's a random forest. So it's a tree-based model. So it's building trees. Basically, the gist behind a tree is to take the data set and split it accordingly to a certain criterion, and then doing that again and again to have in order to grow a tree that will have some sort of predicting power of the data set. And the random forest is doing this not only once, it's doing this many times. So it's growing many trees. So that's why it's a forest. And then it's ensembling the tree, so it's making an average of all the trees together. And there is one last feature of random forest, is that it tries to have non-correlated trees. So if you are building a tree that is meant to minimize, let's say, a classification error, so you're trying to predict the labels of stuff, it's probably always going to pick the same features to that leads to the best performance. So basically you are going to end up ensembling, so making an average of trees that are all the same. So if I take a series of ones 20 times here, and I make an average, well, it's going to be 1. So there is no point in averaging that. So random forest basically corrects this feature by randomly taking in the data set some features that are going to be used in the tree. And when it's building another tree, it's going to use a different set of features randomly. So that's how it ensures that there is no low correlations between trees. So I'm using this to predict this sinusoid. So here apparently my R squared is 99.98. If I plot this, indeed that's the result it's giving me. The model is giving me on the 700 first points. Remember that the model is only training on the 700 first points, so it looks pretty good in terms of what it can learn from the data. Now I'm making predictions thanks to the model, and I'm going to compare my predictions and my actual values. Here we go. I'm plotting this. So that's the ground truth. We have the sinusoid from 0 to 1000, and then we are here training the model on the first 700. So the model is giving me this red sinusoid, pretty much perfect, on top of the ground truth. And now I am going to draw my prediction, and what happens? Oof, that's not good. So the model is very capable of seeing the trend and the sinusoid here, but it's not capable of extrapolating it in the future. Okay, maybe if we use another sort of model, we can correct this. So it's still a tree-based model, but it's called XGBoost, and it's basically a boosting method. So boosting is the way, is the fact to use models sequentially. So I grow a model, and then I use this model to compute the error with my labels or my targets, and then I grow a new model. I train a new model on the errors rather than the actual labels, and I do that iteratively. So each time I compute the error, I construct a new model to predict the error, and then I get new errors, and then I construct a new model to predict these errors. So it's recursive, and so it might have a better chance to see clearer in our trends than random forest can do. Let's try it out. So I'm using exactly the same split. Here my error is going to very low. If I plot my training here, I obtain the same as what my initial ground truth was. I make some predictions and I plot the results again. That's the model answer on the training set, and here again, bam, on the validation set, it's incapable of extrapolating the trend. So why I'm showing that to you is just to go back to my point here. Know your objective. What do you want to do? What do you want to forecast? And also know what your model is capable of doing and what your model is capable of not doing. In this very instance, we've seen that trees are not capable of extrapolating any trends. So there is no point in doing regression and trying to forecast what the price is going to be in the future, because it's going always to fail. However, what we can do with these models is do a classification that is telling me either if it's going to go up or go down, because it doesn't need to extrapolate the data with new dates, basically. So let's just do that. Go back to our main modeling exercise. From the data set, we are going to split between test and validation and train sets, so that we are able to see this sort of behavior. With time series, it's very important not to do a random sampling of the validation set, but to keep the chronological properties of your series. So here I'm just splitting first between what I'm going to keep to train my model and what I'm going to keep to see what it can do on real data. So here split data is just getting me back a training set and a test set. From that training set, I'm just going to get rid of the first leading NAs and then see what it looks like. So I have my training set that is ending in 2017, because I've taken 30% out to test out my model afterwards, and I can see that the labels are correctly described. Now you need to know that for random forest implementation in R, the random forest package, you need to give it either 0 or 1. You cannot recognize -1, so I'm just going to change this here. And actually that's the case for XGBoost as well, which we will cover just afterwards. As we said, I've taken out a way to test if the model is any good, but what I'm also willing to do is to take out a part of the training set in order to see if my training is going correctly and if I am getting any insight or any actual value in the model. This is why I'm taking, again, 30% out to validate my model. If I am in front of an analysis or model that I need to make and I have no tools to do so, and I'm asked what's the most naive way you are able to forecast this value, depending if it's regression. So if I'm asked for a value or if I'm asked for a class or a label, The naive way would be to for labeling for classes would be to forecast the highest frequency label. So if I have more ones than minus ones, if I have no clue how to build a model, I will just take the bet that I need to forecast the one, because the one is more frequent in the data than the minus one. So this is what I'm going to use as a benchmark to see if our model has any value. Here we go. Here the one, the label 1, is present 43% of the time in my training set. So I've excluded the validation set. Okay. Sorry, I've excluded the training set. This is in my validation set. So the data that I'm not going to see. If I were to predict these data without seeing them, I know that 43% of the time there is a 1. So my better chance to get it right is to predict minus 1, and I will be right in 66% of the time. 56% of the time, sorry. So this is our benchmark. Let's try to build a model now that we have the benchmark. So I'm running the random forest. I've covered roughly what random forests are doing. Here I'm just passing in which data to train on, what are the classes or the labels I want to predict, and this is my validation set. So what I've put aside, so this is basically the green and black part, what I've put aside in order to test my results. The model has finished training. Here we go. And now I see that the error rate within the model itself, so the training, is pretty low, and even on an OOB basis. So OOB is out of bag. I invite you to check it. It's a pretty clever way to have a sense of the way your model is training by using the data that is not being used by the sampling in the random forest. I'll let you go through that. But we see the most important point here is that on our validation set, our error is actually 1/3. So we get it right 2/3 of the times, which is the confusion matrix showing you you're getting right when it's 0 and 0, and you're going less. So you have like roughly 30% error on this class, and you have slightly more, 40% error on the one class. So it's already better than the naive model, which was basically you would be wrong 43% of the time. Here we're wrong only 33% of the time. So we've increased a bit our predicting power from doing this. What you can do is use in the random forest package, tune random forest in order to see if that brings any value to your modeling. It's going to try the number of trees that you're growing here, number of trees, and it's also going to try different values for the number of features that you're going to use to grow your trees. As I said, random forest is drawing random features from the data set in order to create uncorrelated trees. You can play on that value to fine-tune your model and increase it or decrease it. This is basically what fine-tuning random forest is doing. It's going to try. So it's going to try on the left. So it's going to go 8, 7, 6, and anything on the left for m-try value, and then it's going to try on the right for m-try value. It's going to grow the number of features that we use, 12, 13, 14, 15, and it's going to give you the OOB, so out of bag error in each case. Here it's saying that if you increase it, you can see on the graph here, if you increase it, it looks like it's better, but then it gets worse. So I think we're pretty okay with the 12 features that are used by trees in order to grow a model. Let's just train. So now that I know that the features I want to use is 12 and 800, for example, I'll let you go through more fine-tuning on your side, on your end. but let's use that. I'm going to retrain my model with these parameters, but this time on the full training set, because now I know that I'm not overfitting when I'm using these parameters. So that my model is trained, I am going to predict the values, and then here I get my predictions thanks to my random forest model, and my predictions are going to be fed in Alphien's backtesting engine. So here we're looking at the Brazilian stock, as we said. So here we go. Let's run the backtest and see if the model has any predictive power. Well, it's not perfect. It doesn't have a lot of signals. First of all, it's good though that it's staying long for most of the time when the underlying asset is trending up, because remember that what we saw in the training set that was that the labels were mostly -1s, so it was going down in the training set, but the model is clever enough to understand that the trend has changed and it's going up this time, so it's not too bad. It's actually quite good. And then here it's hesitating. It looks like it needs to short, but it's shorting it and it's losing money. However, here it's correctly predicting the downtrend here. The underlying asset is crashing whilst the model is turning short. That's pretty good. And then it's cutting the short somewhat at the right time, going back long. So it's not too bad actually. Our model is more efficient than the naive buy and hold. It has some value, and it's avoiding us this big drawdown. We need to keep in mind that we are training on 3 months return, so 3 months trends. So when you have very short trends here, it's not very surprising that the model is not predicting them. And it's pretty good that it's managing to get things that are lasting from basically it's turning from January to April. So roughly the 3 months that we were targeting. So it's not too bad. It's actually quite good. So can we try and improve that with a new model? Let's try XGBoost and see if the results are different. So again, in XGBoost, I've done exactly the same. I've split the data between training and what I've called validation, and it's only training on the first part of the data, and then it's validating it, or we will validate it with the second part of the data. So I've run it, and this is what it's actually telling you. This is the error, so 2% error in the first part, the training set, and here your error is actually 50%. So let's keep this in mind. On the left, on the data we see, we have like initially very quickly 2% error, but in data we don't see, it's random. The model has actually 0 power. It's like a flip of the coin. However, it's during the training here, it's not only learning on the training error, but it's also looking like it's getting down on the test set. So again, the accuracy is not great because it's 40%. So you're right only 3/5 of the time, but it is better than a coin flip. Let's visualize these facts. So here, this is what your model looks like when you look at the data. So obviously, it has a tendency to learn a lot from the data. It's called overfitting. And if you keep out the correct part of the training of the training set as validation, you see that the performance are much more complicated. You know that the model cannot go much below 0.4, so 40% error rate. I've played a bit with fine tuning and changing the parameters, and it doesn't get much better really. So this is it. Let's run it with basically parameters. So I'm only going to run 200 epochs and get the results for that model and see what it gives us in the backtest. So this is trained. I'm getting my predictions, and then I'm backtesting it. It's roughly the same results really than the random forest. It's pretty much the same behavior. So it looks like from tree-based models, I'm not going to get much better than this. So there are a few options you can follow. Either you add more features, or you change the model and you use models that can have time implications or time features in their inputs, such as recurrent neural networks or LSTM. That's just the derivative of RNN, and that might bring you a bit more value and a bit more a higher accuracy, basically. I just wanted to show very quickly what happens when you don't follow what I've said here in my presentation, that the train, validation, and test set are correctly chosen. If I just use this technique where I randomly get rid of values in my training set, I can do it here. I'm just commenting out these two lines, which is saying that my validation set should be following like chronologically following my training set. I'm training, and here the results are totally different. Here I have 4% error on my training set, but it's telling me that I'm accurate 8% of the time on the validation set. Most importantly, it's going down. So if I'm doing it incorrectly, I believe that my error in real life is only 3.5%. I'm like, oh great, all the rest of the time I'm correct. And if you train a model like this and you put it in production and then you start live trading on it, and your strategy is going to have results that are going to be dramatically different from what you expect, because this is classic overfitting, and your model has actually zero value or actually it probably has maybe a bit of value, but not as much as you think in real conditions.